So let's take a look at a quick example involving applying a surge arrestor. And so these scenarios start off kind of similar to what you would see when you're doing like transient analysis, where you need to do the analysis first, the overvoltage, and then you figure out the impact of the surge arrestor. And so what I have is I've got a scenario that's shown in this example where I've got an overhead line and I've got a cable, and basically I've got a surge traveling down the overhead line. A piece of this is going to get refracted into the cable, and this cable's got a length of 500 feet. And what I'm trying to figure out in this case is what am I going to see at the far end when I put the surge arrestor in. And so let's suppose the surge is just 1000 kV square pulse with duration of 2 microseconds. So I've got the surge impedance shown here. These are actually going down the phase conductors. The velocity of propagation on the cable is 400 feet per microsecond. So when I go back to the problem statement, what I want to do is I want to plot the voltage at the load end at point number 2. And then I want to do this with and without the surge arrestor so I can see what the benefit would be. And for the surge arrestor, I've got the IB characteristics such that the reference voltage is 20,000 volts. So if I take V divided by 20,000 to the power of 30, multiply that by 500, and that's going to give me the current going through the surge arrestor. And so this is what the surge arrestor is going to be diverting. So when I work this out, it's pretty basic math in this case as far as the similarity to what we've done before. What you would do is you would start off by calculating the travel time for the cable. It's the length divided by the velocity. So if we have 500 feet divided by 400 feet per microsecond, we got a time it takes for the waveform to go down the cable of 2.5 microseconds. So we got the 1000 kV waveform coming in on the overhead, and what's going to get on the cable? Well, it's going to be the refraction coefficient times this 1000 kV. So the refraction coefficient in this case is gamma B. 2 times 50 divided by 400 plus 50 is 0.222. So the 1000 kV times 0.222 is what's going to be coming down the cable in this particular case. It's just not wanting to cooperate today. So anyway, we've got that 222 kV coming down the cable. And then we're going to get a reflection at the load end. And so if the load's an open circuit, it has an effective impedance of infinity. So if I take ZB minus ZA, that's going to be infinity minus 50 divided by infinity plus 50, which is equal to 1. And what I'm going to get reflected back is 222 kV. So this is the classical open circuit voltage doubling effect, right? Where basically we got 222 kV coming in plus a 222 kV that gets reflected. What I'm going to be getting as a result of this is going to be the 444 kV. And so at the far right hand side, if time equals 0, corresponds to when I have the wave hit the left side of the cable, then basically I see something at the device I'm trying to protect at 1.25 microseconds. And then basically given that I'm going to have just a 2 microsecond waveform, and I'm going to see this kind of look like a square pulse, which drops down to 3.25. Now, after I get the reflection back from the far end of the cable, from the left side of the cable, I'm going to see another square pulse to the right, but I'm not showing that. I'm only going to plot this out to what happens in the first 3.5 microseconds. So this is what we get when we have no surge arrestor. So how do we go ahead and work this particular problem? Well, the equivalent circuit is seen by the surge arrestor, given that open circuit's not going to play a role in the analysis. here is going to be that if I got a 445 kV voltage, then this voltage behind the 50 ohm surge impedance of the cable is the Thevenin, kind of like the Thevenin equivalent of what the surge arrestor sees. So if I put the surge arrestor in, and this has a characteristic given by 500 times the quantity V divided by 20,000 to the power of 30, the intersection of this load line curve with the IB characteristic of the surge arrestor, this intersection right here is what I need to find, right? So the load line starts at 444 kV. If I divide that through by 50, I get 8.88 Ka. The solution's got to be somewhere on this line, and I need to figure out what this intersection is. How do we get that intersection? Well, there's a couple ways you can do it. One would be that if you just do this graphically, just go out and get some plotting paper, or just put this on plotting paper, and you kind of eyeball where this intersection is. And you can kind of see this is going to be kind of close to 22,000 volts. And so basically, whereas I would have had 440 kV, what the surge arrestor is going to do, it's going to knock this down to 22 kV. If I wanted to do this more analytically, how would I do this? Well, what I can do is I've got an expression for current for the surge arrestor, 500 times the quantity V divided by 20,000 to the power of 30. And I can set that equal to the right-hand side, the expression for the current as obtained from this load line curve. And what I do is I equate these two together, and what I do is I solve for voltage. If you take the term on the left minus the term on the right, you get this function of voltage, which is set equal to 0. And what I would do then is I would solve for V. Now, it's obviously nonlinear, right? So how do you solve something like this? Well, what you could use is what's referred to as a Newton-Raphson technique. This is exactly the same technique we would use if we're doing like power flows. So there's an update equation for the Newton-Raphson technique where if you take a guess for Vn and you subtract off this function evaluated Vn divided by the derivative, this gives you an update for Vn plus 1. And you just iteratively go through and you solve this and you get a more exact answer. So I've written a small little program here for doing this, and my initial guess is 21,000. And then basically what I do is I have a function defined. In this case, my voltage is in terms of x. I calculate the derivative of that. And then basically what I would do is I would do this update. This new voltage is equal to the old voltage minus F evaluated the current value of V divided by the derivative of F evaluated the current value of V. And I just iteratively go through until I actually converge to a solution. And I've just kind of used a convergence, came up with a convergence criteria in this case. But if you go through and you solve it this way, you see you get this value 21,975.7. And so anyway, that's going to be the voltage to which the surge arrestor is actually going to be clamping. So next what I'll do is I'll show some examples and how we can do some of this analysis in PSCAD, because obviously this gets kind of time consuming, when we have these nonlinear characteristics for surge arrestors to kind of work these sort of problems by hand.